if we've got the natural log of x, the derivative is 1 on x. We're going to have a look at why is that the case. And then we're going to further use the chain rule to get a generalization of if we've got a function within the natural log, we've got that general expression there. So in order to find out why, we're going to have a look at a few things that we know first. We know that if we've got y equals e to the power of x, then the derivative is e to the power of x. We know that also if we've got y equals log base e of x, then e to the power of y is equal to x. This indicates to us that there is a inverse relationship between exponents and logs. And if we want to understand what we mean by inverse relationship geometrically, what that's telling us is if we were to reflect the exponential function over the line y equals x, then what we would get is the exact curve for the natural log of x. What that also indicates to us is that if we pick a coordinate point on the function of the exponential, you've got an xy point. If you flip the x and the y point and you interpret it on the log function, that gives you a coordinate point on that function. So that's what an inverse relationship is telling us geometrically. What we want to look for here is, given that we've got the natural log of x as a function, what is the derivative of that function? And now I'm going to just use this inverse relationship to help us establish the derivative. And so if we know if we've got y equals natural log of x, that is the equivalent thing of writing e to the power of y equals x. But I'm going to use this guy here, e to the power of y equals x, because I know how to deal with the derivatives of exponentials. If we have a look at the rate of change on the exponential function, we've seen this before. If we take a small change in x, and we also have a look at a small change in y, we know the derivative of that is going to be e to the x. But I want to have a look at what happens to the function e to the power of y, because that is the same thing as the natural log of x. And so as we can see here, if we flip these small changes in x and y about the line y equals x, what we notice is that it represents the exact same small changes on our logarithmic function, where the dy, or the small change in y, now represents dx, and the small change in x now represents dy. And so this tells us something that we can definitely use. Okay, so it tells us that the rate of change of our exponential function is the inverse rate of change of the log function. And so I think it'll help if we just see some numbers here. Let's just pretend that if we were to draw, and I'll do this in a orange here, this slope here, and if I were to say m, the small change in y and x had a ratio of 3 to 1, then what this is going to tell me on my inverse rate of change is that I would have 1 over 3. And we can actually express this as, if we've got dy of dx of e to the x, I know that that is equal to e to the x. If we follow this same logic, that then tells us that if we've got dy of dx of e to the power of y, that's going to equal 1 over e to the y, because it is the inverse rate of change. Using a little bit of a substitution here, we can see that e to the power of y is equal to x from that there. So instead of writing 1 over e to the power of y, I'm going to write 1 over x. And I knew that e to the power of y as a function was equivalent to the natural log of x. So I can then follow up and I can say, well then, dy of dx of the natural log of x is equal to 1 over x. And so this gives us exactly what we were looking for here, which is if we've got the natural log of x, we take the derivative, what we get is 1 over x. And this should make sense geometrically if we just have a look at the graph of the natural log of x and its derivative, which is a hyperbola, and you have a look at the gradient of the natural log of x and the y values of a hyperbola, they match up perfectly. So geometrically, it makes sense to get that result. We're going to extend our differentiation skills here by using the chain rule. So let's say, for example, we've got the function y is equal to the natural log of x squared minus 5. What I'm going to do here to differentiate this, I'm going to let u equal what's on the inside, which is x squared minus 5. This will tell me that I've got y equals the natural log of u. If I differentiate these respectively, I get dy dx is equal to 2x, and I get dy of du is equal to 1 over u. And if I apply my chain rule here, I can see that this is dy du, and this is du dx. So therefore, my derivative, or dy of dx, is equal to the product of these two, which would be 1 over u multiplied by 2x. I'd throw that 2x on the numerator, the u would go on the denominator, and the u was the original function. Okay, and so this will help us generalize here. So if we have got a function within the natural log of x, what we notice here is our pattern was the derivative, or dy dx, was equal to, and I'll point out some different colors here. We took the inside function, which was x squared minus 5, we differentiate that, we got the numerator of our derivative term, and what was originally in the inside was on the denominator. So the pattern here that we're following is that we take the derivative function, we write it on the top, and on the bottom we've got our function that was originally on the inside. And so that's how we can generalize for differentiating natural log. And then we can apply this with our other class of functions. And so here we've got a little bit of a trickier one. We've got differentiate, and we've got a trig function, and we've got it multiplied by a log function. And in order to differentiate this, I would say that I would find y prime, or the derivative, by the chain rule and product rule, because I've got a product of two different classes of functions here. And so this is going to be my u, and this is going to be my v. And in order to find my u primes and my v primes, I'm going to need to use the chain rule. So I can find my u prime by using the chain rule, and if I differentiate what's on the inside here, that's going to be 2x. So 2x times by 3 is going to give me 6x. The derivative of cos is negative sign. Let me say times by negative sign. I'll clean it up in the next line. And x squared stays on the inside, so I can say that's equal to negative 6x sine of x squared. My v prime here, I know that I've got a function within the log. So what I'm going to do is I'm going to differentiate the inside function, which is 3, write it over 3x minus 1, which was the function on the inside. So I've derived my log function. Again, both of these was through the chain rule. From there to there, chain rule. I can then say that I've got my derivative is equal to u prime v plus v prime u. Okay, and that there would give us our derivative function, because that cannot be simplified any further.